we're talking about electrochemical cells, which are called voltaic cells, also called galvanic cells, also called batteries. And these are all spontaneous chemical reactions that result in the transfer of electrons. We separated the half reactions so that we could actually use the electrons and then return the electrons to the other half reaction. And now I want to start to relate those cell potentials. So again, the E cell naught is the standard cell potential. So that's at 25 degrees Celsius, 1 molar for the solutions, and 1 atmosphere of gases are involved. And we've already discussed that N is the number of moles that are transferred in the chemical reaction. So that's going to be when we balance the chemical reactions and we cancel the number of moles that are equal in both half reactions. That's the value of N. So that's the moles of electrons transferred. And then F was just a constant, and that was just the Faraday constant. That was just the Faraday constant, which is the charge on a single mole of electrons, and that's 96,500 coulombs, again, per mole of electron. And that's equal to the free energy. Okay, so again, the negative value indicating that, again, when the cell potential is positive, we have a spontaneous reaction. But for the reaction to be spontaneous in terms of the free energy, it has to be negative. And so that's where this equation comes from. So again, E cell must be positive then for a spontaneous reaction to occur. And of course, what spontaneous means in chemistry is that the products are favored over the reactants. The reaction is going to proceed in the forward direction. So now remember, we already said that the free energy is equal to the maximum amount of work that we can get out of a chemical system. And so it goes to say then that the maximum amount of work for an electrochemical system or a battery, for that matter, then is simply going to be equal to the negative, the number of moles of electrons transferred, Faraday's constant, and then the cell potential. And again, notice that I don't put the naught here this time because it could be for a standard cell. This could be E cell naught. But again, in most cases, we're not working from an equilibrium position. At an equilibrium position, the battery's dead. There's 0 volts. Remember, equilibrium is the end of the reaction. Okay, so when equilibrium is reached, your battery is dead. You'll get 0 volts out of the battery itself. So let's do an example. So using electrode potentials, we calculate the maximum amount of work that can be achieved when 5 grams of nickel reacts with excess oxygen in an acidic solution. So the nickel reacts with the oxygen in an acidic solution to produce nickel 2 plus and water. So first thing we got to do, of course, we need to determine N, the number of moles of electrons transferred, and we got to calculate the cell potential. So we have to first assign the oxidation numbers. Of course, this is pure nickel. Again, you can see it's nickel and the charge on it is 0. So the oxidation state is 0. Oxygen, again, this is the elemental form. This is how it exists in nature. Again, you can see there's no charge, it's 0. Okay, and it's not a salt or anything. It's a pure compound, an elemental compound, only one element involved here. So it's going to be 0. This is a monatomic ion, one atom with a charge. So its charge is going to be equal to its oxidation state. So it'll be +1. Again, we have another monatomic atom, a single atom with a charge. And so the charge is equal to the oxidation state. For water, now we have a molecular compound, and we're going to have to use our rules for assigning oxidation numbers. And we know, according to the rule for hydrogen, hydrogen is generally +1 unless it's a metal hydride. In which case it would be -1, but this isn't a metal hydride. This is a non-metal, so it's molecular. So that's going to be +1, and of course oxygen then is going to be -2 according to the rules for assigning oxidation numbers. Our next step then is to split the reaction into the oxidation half reaction and the reduction half reaction. So in oxidation, the oxidation number increases. So we can see the nickel goes from 0 and it's increased to +2. So that must be our oxidation half reaction, the nickel going to nickel +2. Okay. And then to balance it, of course, we're going to add 2 electrons to it. And then for the oxidation, I'm sorry, the reduction half reaction, we have oxygen going from 0, its oxidation number is reduced to -2. The hydrogen remains the same, so it's the oxygen that we're worried about. So it's going to be O2 going to water, and that's going to be the reduction half reaction. Now, when it's fully balanced, it's going to look like this. It's going to look like this, where we have O2 plus 4 hydrogen ions going to 2H2O. That gives us a 4 plus charge. This is 0, so we're going to add 4 electrons, so that's 0 as well. So again, it was just balancing our redox reaction as we normally do. Okay, so now we got to multiply the coefficients by 2 because we need the number of electrons to cancel whenever we add these two together. So that's going to give us our 4 electrons. Now, when we add them, those 4 electrons are going to cancel, and that is going to be N. That's the number of moles of electrons that are going to be transferred. Okay. Okay, so now we have our balanced chemical reaction. We know the number of moles of electrons that are being transferred. We're going to need to calculate the cell potential. And again, this is going to be from the reduction potentials of both the cathode and the anode. Of course, the anode is where oxidation occurs, and the cathode is where reduction occurs. So we're going to look up in a table, and we're going to look up this reaction, except we're going to flip it. And again, we're not going to be looking for 2 nickel going to 2 nickel 2 plus to 4 electrons. We're going to be looking for nickel 2 plus 2 electrons going to nickel. So without multiplying the coefficients, that's what we're going to look up in the table. The opposite of this reaction, and again, would have to divide through by 2. Okay, so when we look up those values, we find the reduction potential for nickel 2 plus 2 electrons going to nickel at -0.23 volts. And for the oxygen in an acidic solution going to water, it's 1.23 volts. So again, this is our cathode, so that's going to be the 1.23 volts, and this is our anode, so that's going to be the -0.23 volts. Again, this is the reduction potential of the anode. So we're going to plug that in. And that's going to then give us a value of 1.46 volts. Okay. Okay, so now that we have the value of N and we have the standard cell potential, we can now plug it in to determine the free energy, which again really is the maximum work, right? So the free energy then is going to be -N, N being the number of moles of electrons transferred. And so the 4 moles of electrons, the Faraday's constant, which is the 96,500 coulombs per mole of electron, and then the standard cell potential, since this is under standard conditions, which would be 1.46 volts. So we can see the moles of electrons cancel. Okay, that gives us -5.6 times 10 to the 5th coulomb volts, but we know that a coulomb volt is equal to a joule. So the coulomb volts will cancel, and that'll give us the free energy as -5.6 times 10 to the 5th joules. Now, again, remember this also equals the maximum amount of work, but this was for this balanced equation. So in other words, this was for 2 moles of nickel, not 5 grams of nickel. So to determine the maximum work, we're going to have to convert this into a balanced thermochemical equation. Right? So we're just going to say that this whole thing is del G is equal to -564. Now we could relate the moles of nickel to the free energy that is released to the 5 grams, right? So again, we'll start off with the 5 grams, okay? Okay, so maximum work then is going to be the 5 grams of the nickel. We need to convert that to moles, so we could use the molar energy ratio. So we'll divide that by the molar mass of nickel. The grams are going to cancel. I can see for every 2 moles of nickel consumed, 564 kilojoules of energy is released. So the moles of nickel cancel, and that gives us a value of negative 24 kilojoules. Okay, so that's the maximum work. So in other words, there's 24 kilojoules of energy available for work. Okay. Then we're going to start relating things like free energy to our cell potentials. So free energy is going to be equal to N, and this N is going to be the number of moles of electrons transferred in the redox reaction. Again, that's going to be the number, that's going to be the moles of electrons when we're balanced in a chemical reaction that cancel. So that's N is going to be the number of moles of electrons. F, of course, is just the Faraday's constant. And Faraday's constant, again, is simply the charge on 1 mole of electrons. And I only need you to know this to 3 sig figs. That's 96,500 coulombs. And that is per mole of electron. Okay. And then finally, we're going to multiply that. Since this is the standard free energy change, we're going to use the standard cell potential. If this wasn't the standard cell potential and was just E cell, this would just be del G with no naught. Okay. Then, of course, we know that del G actually represents the maximum work. So we could say the maximum work is simply equal to NF E cell. Okay. Since we know that del G is equal to maximum work. Let's try another. So number 42 says, calculate the standard EMF at 25 degrees Celsius for the following cell reaction from the standard free energies of formation. Compare this to the standard EMF calculated from the standard reduction potentials. Note that all these things can be found in tables of chemical data. Okay. Okay, so we have our reaction, and we want to calculate this. We want to calculate the free energy of formation. So del G. I want to calculate del G. How am I going to calculate del G? Can I calculate that? Do I have to do the del H and del S values?
No.
Why not?
Because it's at a standard 25 degrees Celsius.
Yeah, it's at 25, so I just need to use the free enthalpies of formation. I don't need to do both of them and basically take 3 times as long to get the same value. Okay, so I'm going to look these up in the table. So right off the bat, again, since I understand what free energies of formation are, in its elemental form, it has to be 0, so I don't even need to look that up. I will need to look up the copper 2 plus, which is 65.5 kilojoules per mole. I will need to look up the aluminum 3 plus, which is negative 485 kilojoules per mole. And again, I can see copper, that is its elemental form, right? At 25 degrees Celsius in 1 atmosphere, copper is monatomic and it's a solid. It's black on a periodic table, so I know too that it's 0. Or you can look it up. It just takes longer, okay? So I'm going to calculate my free energy then. That's just going to be the sum of the products, each multiplied by the coefficient in the balanced chemical equation. So we have our 2 moles of aluminum 3 plus, and that's times negative 485 kilojoules per mole. And then plus 0, we don't really care about that. And then minus, again, we have 0 for the aluminum, and then plus our 3 moles of copper 2 plus at 65.5 kilojoules per mole. So all the moles cancel. Plug that into your calculator, and you're going to get a free energy change of negative 1,166.5 kilojoules. Okay. That's going to end up being 2, 1 in front, because this is going to put it 1 in front. Okay, so any questions about that? Okay, now how am I going to calculate the free energy formation from, I'm sorry, how am I going to calculate the standard EMF for this cell from the free energy? How am I going to do that? Oh, excuse me.
Would you first find the half reactions?
Okay. So what is my 2 half reactions then? What's my oxidation half reaction?
The AL.
So aluminum's going from 0 to 3 plus, so that's oxidized. So aluminum to aluminum 3 plus. Okay. And the reduction?
It would be Cu 2 plus to Cu.
Okay. So I want to use del G to get E cell naught. I want to use del G to get E cell naught. How am I going to do that? How am I going to use del G to get E cell naught? Is there any relationship between del G and E cell naught?
Del G is equal to negative NF E cell naught.
Okay, so I can get E cell naught by simply rearranging this equation, right? So del G over negative NF. Well, I know del G. Del G is negative 1,166.5 kilojoules. I have negative, how many moles of electrons, right? N is the moles of electrons. How many moles of electrons?
You have to balance the oxidation and reduction halves.
Okay, so how do I balance the oxidation?
Add 3 electrons to the right.
Okay, and the reduction?
Add 2 electrons to the left.
Again, if you have any questions of why, just stop me. Okay, now what?
And then multiply it so the electrons are the same. So 2 and then 3 respectively.
So that's going to give us 2 aluminum plus 2, going to 2 aluminum 3 plus 6 electrons. And then here we have 3 copper 2 plus 6 electrons going to 3 copper. Okay, how did that help us?
The moles of electron is equal to 6 because that's canceling.
Right? So N equals 6 mole of electrons. So this is 6 moles of electrons. What is F?
It's Faraday's constant.
Yep, do you remember the value?
965, 96,500.
It's 1,000 actually, right? 96,500. Okay. And you remember the units.
Coulombs per mole
Right?
of electrons.
Yep, that's the
80.
charge on a mole of electrons. So the moles of electrons cancel. Okay. What units do I expect for E cell naught? Right now I have kilojoules per coulomb. What units do I expect for E cell naught? Katrin, what do you think? What units do I expect for E cell naught?
Volts.
Yeah, volts, right? We don't have volts yet. Can you think of any relationship with volts and either joules or coulombs? Well, remember, 1 joule is 1 coulomb volt, right? So 1 joule is 1 coulomb volt. So first off, this is going to have to be in joules. So I'm going to have to multiply this by 1,000 so that I got joules. And then 1 joule is equal to 1 coulomb volt. So the joules cancel, my coulombs cancel, and now I have volts. So plug all of that into your calculator, and you're going to get 2.014 volts. This will be 3 sig figs, since that's what it's 4. This must be actually be 3 sig figs. Anyway, so this is going to be 2.014 volts. Okay. Okay, now the second part says, well, calculate that by comparing it to the E cell naught that you get from the standard reduction potentials. How can we get E cell naught from the standard reduction potentials? How do we get E cell naught from the standard reduction potentials? Anybody, how are we going to get E cell naught from our standard reduction potentials? We've done it many, many times.
Is it like what we did in the last problem with the E cell of the cathode minus E cell of the anode?
Yeah, right? These are the standard reduction potentials. So which one is my anode?
The anode is aluminum.
Yeah, oxidation is the anode and reduction is the cathode. Okay, what would be my next step?
Find the E cell for each of them in the tables.
Yeah, right. So I'd look that up. This is going to be negative 1.66 volts for the aluminum and positive 0.34 volts for the copper. So therefore, if my cathode is 0.34 volts and my anode is negative 1.66 volts, so that's going to give me what? 1, and then we have, so that's going to be 2.00 volts. So basically identical to what we found using the free energies. Okay. So would this represent a galvanic cell or an electrolytic cell? So would this represent a galvanic cell or an electrolytic cell? What do you think? Hannah, what do you think? Would this represent a galvanic cell or an electrolytic cell?
I think it would be galvanic,
Why?
but I see that there's the the two solids that could work as the electrodes, and then
Nope.
the aqueous solution.
Nope.
No?
Nothing to do with solids, liquids, aqueous solutions, nothing at all to do with that. Batteries generally don't even have aqueous liquids, right? It has everything to do with this. What am I referring to?
They're positive.
It's positive. Remember, galvanic, voltaic cells, batteries, they're all spontaneous reactions. An electrolytic cell is non-spontaneous, so this would be negative. So does that make sense? It's basically just trying to make sure that you understand that electrolytic cells are non-spontaneous and would have a negative volt for an overall cell reaction.
Wait, did you say non-spontaneous would be negative?
Yeah, negative, right? Again, look here, look at the equation. So this is the perfect time to look at that, right? We know del G has to be negative to be spontaneous, right? So if del G needs to be negative and there's a negative in this equation, that means E cell has to be positive to be spontaneous. So does that make sense? Excuse me. And so it says, calculate the maximum work available from 25 grams of aluminum in the following galvanic cell, assuming that there's an unlimited supply of acid and gaseous oxygen and the cell is maintained under standard conditions. Note that O2 is reduced to H2O. Okay, so how do we calculate maximum work? What is maximum work? What is maximum work?
Delta G.
Delta G, right? So we're going to need delta G. So how am I going to get delta G from all of this stuff here, this electrochemical stuff?
You have to do 2 half reactions.
Okay, that would definitely going to have to do that. But what is the relationship between del G or max work? So what's the relationship between these and the electrochemical values? Again, I strongly suggest, I would have hoped that over the weekend the Ians would have done all of this homework. So the relationship then, del G is simply equal to negative the number of moles transferred, the Faraday's constant, and the cell potential. In this case, it's a standard cell, so it is just going to, it's under standard condition. So it is just going to be a standard cell. So it would look like that. Okay. So then we're going to need to calculate the cell potential, and we're going to need to know the number of electrons transferred in this reaction. So we definitely will have to start off with writing the half reactions to get the cell potential and the number of moles of electrons transferred. But more importantly than that, we're actually going to have to write a balanced thermochemical equation to relate del G to the number of moles of aluminum. Right? That's the only way we're going to be able to relate the two, are these balanced thermochemical equations, so then we can use the molar energy ratio from that balanced thermochemical equation. So we'll start with the oxidation half reaction. And of course, the oxidation half reaction occurs at the anode. And so that's going to be the left side of the equation, and it's got to be oxidation, so the oxidation number must increase. So that must be aluminum going to aluminum 3+. We want to balance, so it's already mass balanced. There's only one aluminum. We have a +3 charge over here and a charge of 0 over here. So we would have to add the 3 electrons to that side so that we have a balanced half reaction, both charge and mass balanced. Next, we have this one over here. We have the H+ and O2. So this is going to be our cathode. So this will be our cathode. And so this, of course, is the reduction half reaction. And so the reduction half reaction, and it's saying water. It says O2 is reduced to water. So it's already telling us what we need to do. It's saying that O2 is reduced to water. And then we just need to balance it after that. So we balance the oxygen by adding waters. There's 2 oxygens here. There's 1 here. So we'll put an extra water. So there's now 2 waters. Then we balance the hydrogen by adding hydrogen ions. So 2 times 2 is 4. So there's going to be 4 hydrogen ions. And then charge, this side is 0 because it's all neutrals. This side is 4+. So I'll have to add 4 electrons to this side. Now, of course, we need to add the 2 half reactions together, so we need the electrons to cancel. So if this is 3 and this is 4, well, the lowest common denominator is just 12. So I'll have to multiply this by 4. I'll have to multiply this one by 3. And so that's going to give me my 4 aluminum going to 4 Al3+ plus 12 electrons. And then this guy here is going to be 12 electrons plus 12 hydrogen ions plus 3 oxygens going to 6 H2O. Now we could add them. The 12 electrons cancel. That, of course, means there's 12 moles of electrons being transferred in this equation. That's our N value. And our final equation then is the 4 aluminum plus the 12 hydrogen ions plus the 3 oxygen going to 4 aluminum 3+ plus 6 H2O. Okay. Okay, so there's our balanced chemical reaction. We're going to need the E cell, so we're going to have to look up the reduction potentials for both the aluminum and the oxygen going to water. So now remember, these are going to be reduction reactions, so it'll be the opposite of this is what I'm going to look up. It'll be the aluminum 3+ plus the 3 electrons going to aluminum, right? And you're just going to get those out of your tables. So this is the one for the exam, right? So there's the aluminum 3+, so that was negative 1.66 volts. And again, these are the standard reduction potentials. And then we need the oxygen going to water. So looking down this table, okay, that's not on this table, but it is in the table of chemical data, okay? So it is in the tables of chemical data, and when you look it up, it's 1.23 volts. And so our standard E cell, right? Our standard E cell then is the reduction potential of the cathode minus the reduction potential at the anode. So that's going to be equal to, so our cathode is 1.23 volts. Whoops. It's 1.23 volts, and then we're going to subtract the negative 1.66 volts. And so that's going to give me what? So 2.89 volts. So now we have our standard cell potential. Now we could find del G. So del G then is simply going to be equal to negative the number of moles of electrons transferred, which we determined was 12. Faraday's constant, which is just the charge on 1 mole of electrons, that's 96,500 coulombs per mole of electrons. Our moles of electrons cancel. And then our E cell, which is 2.89 volts. But of course, del G is in joules or kilojoules. So I know that in 1 joule, there is 1 coulomb volt. So the coulomb volts cancel, and that leaves us with our units of joules. You would multiply this out, and that will give us a value of negative 3.3466 times 10 to the 6th joules. If I want this in kilojoules, I'll just divide this by 1,000, so negative 3.34, and this is 3 sig figs, 66 times 10 to the 3rd kilojoules. Okay. Okay, now we know del G. So this is our del G. Del G is equal to negative 3,346.6 kilojoules. And now finally, we could actually answer the problem. Maximum work for 25 grams of aluminum, aluminum being the limiting reagent. So the maximum work then is simply going to be del G for that 25 grams. So it'll be 25 grams. It'll be 25 grams of aluminum. You need to convert aluminum to moles. So just look up the molar mass on the periodic table. In 1 mole of aluminum, there is 26.9815 grams of aluminum. The grams of aluminum cancel. Now that we have moles, we could use the balanced thermochemical equation to relate the moles of aluminum, and we need that to cancel, so that's going to be in the denominator. And we could say for every 4 moles of aluminum consumed, 3,346 kilojoules of energy is released. So our moles of aluminum now cancel. Plug that into your calculator, and that's going to be negative 775.21 kilojoules to 3 sig figs, or negative 775 kilojoules of energy is available for work.